Hello, this is lesson 8 of the Calc A review, and the topic today is concavity. Let's look at this first setup here. Actually, a definition, a graph of a function, we call it concave up on an open interval. If y prime is increasing, y prime is a derivative. For any function, even a derivative, to be increasing, that means its own derivative is positive. So now we're talking about a second derivative being positive. Okay, and that's perhaps the most common way we look for concavity is we look at that second derivative being positive or negative. Concave down, if y prime is decreasing or y double prime is negative on an interval. Without a graph, we can analyze y double prime to learn about concavity. Find the first derivative, find the second derivative, and we can plug in points there. Point of inflection, by definition, is a point where the graph of a function has a tangent line. That part is often overlooked, but the function has a tangent line and the concavity changes. Okay, we're going to see some interesting special cases where you have a change in concavity, but it's not actually classified as a point of inflection. At a point of inflection, a second derivative will be either 0 or undefined. And my copy got cut off here, but it says the converse is not necessarily true. There must be a tangent line at a point to be considered a point of inflection. Example 1. Graph of f is given, find x values that meet certain criteria. Where do we see a change in concavity? Starting from the very left, curve appears to be concave up, and then right here changes to concave down. So I'm just estimating, I put around 1.5. We're concave down, concave down, concave down. Right here, we switch back to concave up. I called that approximately 4.75. Now, something is happening with concavity right at this location that I'm hovering on, but we switched to a straight line segment, which isn't considered to have a concavity. So I didn't include that as a place where concavity changes. Same thing at this next corner cusp hybrid. Although I guess informally, yes, there is some kind of change occurring because you're switching to no concavity and then back to concave up. But the next location where we switch from up to down is right around here, around 8.8. Here's the special case. We do switch from concave down to concave up, right? But it's not a point of inflection because we don't have a tangent line here. But we can say concavity changes, so I indicated that with the 9.8. And then there's one more up here, close to 11. I put about 10.8. So yeah, we can tell concavity from a graph. I kind of overlooked the picture up at the top of the page, but it just reminds you that if your curvature is heading down, you're concave down. If your piece of your curve is curving up, well, that's concave up. Example 8.2, this time we'll use a table to answer questions about a function f, and I apologize for discrepancies here. There seems to be a switching between little f and big F. It's all supposed to be one function. We'll just call it f. Function is continuous from -2 to 9, twice differentiable on -2 to 9, except at x equals 4. Let's see if we can get a sketch. Okay. So from -2 to 1, we know f prime is negative, f double prime is positive. That means your curve is decreasing. It's got a negative slope, but it's got to be concave up. So we just draw a piece of a curve that is decreasing but concave up until we get to 1, where both these derivatives are 0. So we expect a flattening out to a valley there. And then from 1 to 4, we've got positive for both, which means we're still concave up and we're also increasing now. We're drawing that in. Something's happening at 4, the derivatives do not exist, so your graph probably has some kind of corner or cusp. I put the cusp, this shark fin looking phenomenon here. And on the right side of that, we've got negative, negative. So my graph had to be drawn as decreasing, but now concave down. Notice at 6, the second derivative goes to 0. We're still decreasing overall with the negative first derivative, but we've got a second derivative, 0, and we do have a switching concavity. So there's a point of inflection. Still decreasing, but now you're concave up. On that interval, determine the x values where we have relative extrema. That's easier to do now that we have a graph. It looks like at 1, we've got a minimum, 4, we've got a max. Notice the prompt says parentheses, so we're not considering endpoints here. Justify means we have to explain why we picked these values in writing. So I put just where f prime changes sign. X values for a point of inflection, again, justify. We want to find where f has a tangent line and f double prime changes sign. This technically only happens at x equals 6. 8.3, sketch another graph that satisfies all the conditions. Again, I see capital F's and lowercase. It's all meant to be the same function. So this was a little trickier if you're starting from scratch. I know it's easier to see if I already have the answer here, but one thing to do first, I'm looking for actual XY points to plot. F of -1 is 4, so we know -1 comma 4 is a point. 1 comma 0 is a point, and then we're just kind of filling in between those points and on either side, getting information about whether my slopes are positive or negative, whether my second derivative is positive or negative. One thing we notice right away is that f double prime is negative when x is negative, positive when x is positive. That means whatever you draw, it has to be concave down to the left of 0, concave up to the right. And then the last little bits of information, we have indication of maxes and mins at -1 and 1, thanks to the first derivatives going to 0. And then finally, f prime is negative between -1 and 1, positive when you're outside of -1 and 1. So there's really only one way to get all those criteria to work. Example 8.4, finding some things. Also practicing with those justifications. This time we're going with f equals x to the 2/3. Okay. Looking through the list of stuff we're finding, we know we're going to need first and second derivatives eventually, so I've done that work here. You'll notice I've chosen to write my second derivative in that radical form without the negative exponent. That really does help you to see where this thing might be undefined. Okay, it's not necessarily as obvious from the original form that you cannot plug a 0 in. Same thing for our first derivative, actually. Okay, so finding critical points, we want to find where the first derivative was either 0 or undefined, and it's never going to be 0 quite exactly, but it does go undefined at x equals 0. So that's my only critical point, 0, 0. I did have to give an x and a y. It says critical point, not critical number. And then that's my justification. Finding max and min. Okay. It doesn't even specify type, so I guess we have to find all. I said absolute max at 0, 0, since f prime is, oh, that's actually a typo, isn't it? We should say absolute minimum at 0, 0, because we're switching from negative to positive. Okay, that's a minimum there. In fact, let me just make sure everyone is super clear with that. That is a minimum. And that's actually the only one. It's the only one because, well, we don't have any other max or min to speak of because this function doesn't have a given interval to work with. So we're assuming -infinity to infinity. As you go out towards negative infinity, we see that we were always decreasing. So there isn't any highest point. We're coming down, down as we approach zero, but there was no highest point because we were going forever. Same way as we go towards positive infinity, slope is positive, it keeps going up, but it never stops going up. There's no bound for us to stop at. So the only extrema to speak of is the minimum at 0, 0. Increasing, decreasing, again, we justify by talking about what f prime is doing. Okay, so I've written that out here. There are no points of inflection, and we know that because analysis of that second derivative shows us that essentially it's always negative. We never switch concavity. So finally, describing where we were concave up and down. We're never concave up, concave down. I'm not going to include 0 there because, again, the definition of concave down is that your second derivative is negative and second derivative doesn't exist at 0. So it would be technically a mistake to try and say this thing is concave down at 0. If you were to graph this, what's actually happening at 0 is you've got a cusp. All right, let's head on down to the next page. Oh, I believe this is the last page. Another really important, pretty powerful tool for you guys, and we will see this pop back up again second semester in this course with some new stuff as well, but second derivative test for local extrema. There's a way to identify local maxes and mins going off of a second and first derivative. Here are the rules. If your first derivative was 0, at a certain location, x equals c, the second derivative is negative. That's proof that you had a local max. Seems a little counterintuitive to say a value is negative corresponding to a max, but it actually makes sense, especially when you think about trying to draw a curve that has a slope of 0 and yet is concave down. You're drawing the top of a hill, right? So that's your max. And then, flip it around. We're talking about right down here. If f prime is 0 and you're concave up, it's going to be a minimum. And then we've got an example practicing that. Use second derivative tests. Here's an f, simple derivative for f prime, and then again with f double prime. Okay. We set the first derivative equal to 0 to get some candidates for maxes and mins. I see plus or minus 2. I'm going to plug each of those not into the first derivative, but into the second derivative to apply this second derivative test. Here's f double prime of -2, comes out negative, which is, less than 0. We had a max at -2. I give the x and the y. Then f double prime at +2, we get a positive result. That means we had a min, 2, -21. And then there's one more example. It's not really too much different than the previous, a g function. So, try it on your own, check work with mine. Same thing, first derivative, second derivative. Set the first to 0, plug the results into the second, and see what happens. Right here, actually, g double prime is not strictly positive or negative. You actually didn't have an extrema there at all. All right. That concludes lesson 8. Let me know if you have any questions. Thanks for watching.